Today we are talking about geometric applications, applying geometric sequences and series to real-world situations. Okay, so these are the types of problems, just like with arithmetic, that deal with geometric this time. Okay, out there in the real world, population growth, et cetera, et cetera. Okay, now for some of your application situations, you'll need to use this geometric sequence instead of what we already know is our explicit formula. Okay? It says U sub n equals U sub 0, parentheses, 1 plus or minus r to the n power. And this is where U sub 0 is the initial amount. Okay? Depending on the problem and depending on what's given to you, it might say that this population is initially 5,000 people. Okay? That 5,000 is the starting point. It is not the first year's worth of people. Okay? And so when that happens, that means that you're no longer going to have an n minus 1 in your exponent. You're just going to have an n. Okay? So be very careful. Depending on what you're given, you might have to use this one. Okay? However, if you are given the first term, maybe the number of leopards in the first year, if they give you the first term, anything about the first year, anything that represents first, then you'll use the regular explicit formula. Okay? Use the regular explicit formula. So let's look at this first example. When you open it up, okay, it says Penelope is starting her first job. She will earn $24,000 in her first year, and her salary will increase 4% every year. Calculate how much Penelope will earn in her fourth year of work. Now, if she earns $24,000 in the first year, are we going to use the U sub 0 formula, or are we going to use the explicit formula? Explicit. And what tells you that?
First.
That first, okay? So that means that U1 is 24,000. Now her salary is increasing 4% every year. Now this is where you have to be careful. If I'm using the explicit formula and I know there's an R inside of that formula, what is R going to represent? It is. What's that number going to be?
0.04. 0.04.
It won't be 0.04. I thought I heard someone was. It's going to be 1.04 because she's getting 100% of her salary plus a 4% increase, which makes a total of 104% for that following year. Okay? And then what's going to be in this problem?
4 years.
4 years, because we're trying to figure out her fourth year of work. So we are looking for U sub 4, her fourth year of work, knowing that she makes $24,000 her first year. Her salary is increasing by 4%, so that's 1.04 because, again, she's still getting her $24,000. She's just getting an additional 4% on top of that, and then 4 minus 1. So then we'll type that into our calculator and get our answer. And we are talking about money here. So how should we round?
To the nearest cent or dollar?
Not dollar, but to your 2 decimal places. Okay? So reading from left to right, what do I have?
26996.74.
So 26996.74. And this is in dollars. There we go. Questions?
Why is
Because money. Yeah. So anytime we're talking about money, unless it specifies otherwise in the problem, which you usually will say at the very beginning of the question or like the last sentence of that question, it will say round to the nearest dollar, or it might say round to 2 decimal places. If it doesn't say and we're talking about money, 2 decimal places. All right, let's look at this next one. This is a nest of ants initially contains 500 individuals. The population is increasing by 12% each week. How many ants will there be after 10 weeks and after 20 weeks? And then, of course, how many weeks will it take for the ant population to reach 2,000? So, what key word is in this problem?
Initials.
Initially, which means we're going to use the formula that you sub 0, 1. Now that plus or minus basically indicates whether or not you are adding or subtracting these number of ants. What are we doing? A little louder. We're adding. So then that means we're going to basically do 1 plus our rate. Okay. So if I want to figure out how many ants will there be after 10 weeks, that means that 10 is going to represent one part of this formula. N. So I'll have U sub 10 equals 5,000. 1 plus raised to the 10th power. And then I'll type that in and I'll get my number of ants. I'll do a similar process to figure out 20 weeks. It's just instead of 10, I'll do 20. So find out my population after 10 weeks and 20 weeks. Now, I am talking about ants here. Okay? Little bitty creatures. Okay? When you write your answer, you have to take into account that you can't have a fraction of an ant. Just like you can't have a fraction of a person, just like you can't have a fraction of an animal. Okay? So in these particular cases, when you're talking about how many ants, you can't have 0.2. You're going to have to round down. You won't round up because you can't compensate for that part of the ant that doesn't exist. Okay? So you gotta round down. So when you did your 10 weeks, how many ants did you get?
1552.
1552, because I think it was 1.9. So even though it's close, even though it's so close, the rules of rounding don't apply here because we're talking about, I'm not gonna say people, but insects, whole creatures.
What if it's 0.9? Doesn't that just mean like it's missing like a couple hairs or something?
It's missing a couple of hairs, maybe a little leg or something, but still we can't compensate for the fact that it might have got squished or got stuck in the door or something like that. Okay? So, ants, because I want to make sure I include my units.
What kind of ants?
I don't know. I don't like them regardless of what kind they are. Alright, what about the 20 weeks?
4, 8, 2, 3.
4, 8, 2, 3?
Yeah.
Ants, very good. So,
For this interruption.
So, now, how many weeks will it take for the ant population to reach 2,000? Now, this time, we're looking for what part of the formula?
UN. Wait, no. N.
You're looking for N, because N represents the number of weeks. So, we're trying to see how long it will take for the population to reach 2,000. So, then that means I'm going to plug 2,000 in to what part of the formula? U sub N. So, 2,000 equals, what was my initial amount? 500.
Oh.
Then 1 plus my rate raised to the nth power. And just like before, we got to graph this, okay? You setting up the equation will compensate for the work that's involved in solving this problem, okay? If you want, you can go one more step and do what?
Graph.
Well, before you graph. Simplify by distributing.
Subtracting 500.
Not subtracting 500, but dividing by 500. And what's 2,000 divided by 500?
4.
4. So this time, instead of putting 2,000 and having to increase my window very largely, I just can go put 4 in and maybe not have to increase it so much. Okay? So I'm trying to figure out my number of weeks. So in my y equals, I'm going to type in 4 for one of them. And then 1.12 to the what power? X.
And X, yeah.
I'm going to go back to a standard window so I can see 4 easily. So I'm going to go to zoom 6. There's 4. And let's see if this exponential is going to intersect before 10 weeks. Actually, stop.
I did 15.
15? Okay. I'm going to change my window. I'm going to change my what?
Y max.
Y max to 15.
No, I changed my X max to 15.
Oh, your X max to 15. Oh, yeah, that's right, because I watched fine. Okay, X max. There we go. All right. So how do I find that intersection point.
Second trace.
Second trace, option 5, and
Get close to it and then put it
get close. Enter 3 times. 1, 2, 3. And I get
12 point. Yeah, that.
so rounded to 3 significant figures. That's 12.2, and we would leave it at 12.2 because it didn't ask us how many whole weeks. So we round that one to 3 significant figures. When it comes to time, unless it specifies, 3 significant figures. Okay, so 2 things that are very common in geometric sequences in the real world are inflation and depreciation. Okay, these are 2 things that are main in our world. Okay, by definition, inflation is a general increase in the price of goods and services over time. Okay, inflation reduces your purchasing power of your money. Okay, so in other words, when a company makes a whole bunch of iPhones, okay, and people are buying up these iPhones, at a certain point in time, they're going to have too many iPhones and not enough people to buy them. Okay, so the increase of price in goods and services over time, that will be an example of inflation. Okay. Depreciation is a loss in value of an item over time. The biggest example I can give you on that is cars. Okay? When you buy a brand new car, no miles, right off the lot, it's already depreciated in value. Okay? And it will continue to depreciate over time. So let's look at these last 2 examples. Georgia would like to purchase a painting that is currently worth $5,000. She makes monthly deposits into an investment account so that she can purchase the painting in 3 years' time. Now, if inflation averages 2.5% per year, calculate the value of the painting indexed for inflation for 3 years. Okay? That's your wording there. But you have to be able to recognize that this is nothing more than just a geometric sequence problem. Where that $5,000 represents what?
Wait.
0 because currently is initially.
It's the initial amount. This is how much the painting is worth the day she walks into that gallery and is like, oh my goodness, I want to buy this painting. Okay? So that represents use of 0. Now she plans to buy this painting in 3 years' time. So that means that 3 represents what? It represents your N. It's your time. And the inflation averages to 2.5% a year, which means that represents your ratio, but we got to make sure that if it's inflation, is that an increase in price or a decrease in price?
Increase.
It's an increase, so that means it's going to be 1 plus your R as a decimal. What's 2.5% as a decimal?
0.025.
Very good.
Should.
So then we have all of our pieces to basically figure out how much she's basically going to need to have to purchase this painting in 3 years. And she still wants that paint after 3 years, and that must be one amazing painting. So here we go. $5,000, 1 plus R to the 3rd power. And we are talking about money, so we should round to 2 what?
2 decimal points.
2 decimal places. So 2 dp. How much?
5384.45.
Mm-hmm. I'm telling you, it must be a Picasso or something. All right.
Must be 5 Picasso.
But as you can see, inflation causes that price to go up. So that means you just can't walk in there 3 years later and think that it's going to be the exact same amount. Okay, you have to take into account that. All right. And as we wrap up to get to this last problem, the Wednesday's class we're going to be talking about financial applications with geometric and arithmetic sequences and series. And so we're going to be talking a lot about real world stuff. I hope that you guys will enjoy. And that way you know that adulting is hard. Okay, and you enjoy being a child. Okay, or at least in your youth. So here we go. An industrial dishwasher was purchased for 2,400 pounds and depreciated by 15% each year. If it's a depreciation, that means that the cost of the worth of this dishwasher is going down as a decrease, which means that in our formula, we're not going to use 1 plus, we're going to use the subtraction. 24 pounds, 2,400 pounds represents
Money.
the initial amount of money that the dishwasher was worth. We know we're going to have to do 1 minus this to get our rate. And so to find this value after 6 years, that means we're going to plug in what for N? 6 for N, okay? So 6 years with a dishwasher that's costing $2,400 pounds, depreciating at 15%. In 6 years, let's see how much this dishwasher is worth. How much?
905.1 16 pounds.
I missed the
5.
Thank you. So how much did it depreciate? How do I figure that out? Subtract what? And that wouldn't use the answer here. So how much did it depreciate over 6 years? 1494.28. And that's how a lot of these goods, that's how they lose their value. And it is on a rapid basis. I'm telling you, you buy a brand new car, you drive it off the lot, let's say you change your mind. Unless that car dealership has like a 48-hour, return policy that you can get your money back, you're looking at, let's try a $24,000 car that you might only get 16 or 17. You get no accidents, no chips, no nothing. You ain't gonna come back with your money. But that's how we apply geometric sequences to real world.